For assignment 2, you have to take a noisy heart signal, condition it, and generate a pulse for each heartbeat. Shown here is the requirements unique to each one of you, and as you can see, each one of them has a DC component to the signal and then an amplitude which does not include the noise. That's just the pure heart signal. However, what I've given you is the heart signal with the noise superimposed on top of it. So let's quickly look at how that looks. In here I have two CSV files. The one contains only the heart signal. You don't have access to that. And then the other one has the noise superimposed on top of it. So let's quickly look at what those signals look like. As I said, I don't mind at all if you generate extra signals as long as you remove them before you submit. There we go. Okay, so if I then generate these signals, I'm going to plot, just add a plane here. So this is the clean one. As you can see, I have a signal that is of amplitude 19.5 millivolts. And then looking at the superimposed noise, as you can see, that goes a bit beyond those levels. It goes a bit further. So this is the noisy signal and this is the heartbeat signal, and the heartbeat signal has a constant amplitude, so this is very clean. Normally you won't have that, but that's the signal that I've given you. And the signal is supposed to contain the lup dup lup dup lup dup lup dup of the heartbeat. So that's the valves opening and closing, and at the bottom, as I said, superimposed quite a lot of noise. So if we were to analyze this, let's just look at the frequency content of the noisy one. You can see this is what it looks like. So if I just change the color to make it a bit clearer, you can see that we have quite a broad spectrum of information inside that. And I just want to show you this. I vaguely recall I had to change these settings when I did it, so that the FFT showed up clearly. So this shows you the noise and the signal content. So if we were to look at this signal just carefully, you can see if we were to apply a threshold here, let's say you applied a threshold here, the first thing to notice is over here it will create quite a few pulses. So we need to take away those jerky noise signals over there. That's the first thing we need to do. But if you also consider if the threshold was here, that would cause a problem, because many of these beats have an amplitude, if you consider it from the mean of 1 volt, has an amplitude that's quite low, so they won't even register as a beat. So we have this slowly up and down, up and down, up and down motion that's superimposed onto the heartbeat. We need to get rid of that. And then also the jerky, the high frequency noise that we need to get rid of. I just want to show you what my solution looked like. So this is my solution. The noisy signal comes in. Don't mind the signal values at the moment. And then there's a filtered signal, which obviously changes the original signal a bit because of the distortion caused. You can see that's the original. That's not what it looks like anymore. And then I've amplified it, applied a threshold, and after that I've generated the pulses. Each beat results in a pulse. So that's what you have to do as well. Just be sure that you delete these extra noise signals before you go in. So I've given you quite a few signals to work with. Let's just look at that. So I've given you, each one of you, 4 signals, and these signals contains the DC component. I just want to show you it real quick. It contains the DC component and the heartbeat and the noise combined as one. So if you were to plot it, it would look similar to this one here. with your own amplitude and your own DC offset level. If you were to look at the rest, I've also given you a normalized data set. So this is just 10 sets with different noise aspects added to it, and they have been normalized to 100 millivolts. So if you wanted to use one of these, what you have to do, actually I just need to close this one first. What you have to do is to modify this. So if you want to use it, you need to modify it to your own unique specifications. So the first column here is the DC offset. The second column is the noise plus the heart signal, normalized to 100 millivolts, and this is normalized to 1 volts DC, and this is just the sum of the two. So if you wanted to make your own, let's say your specification was 25 millivolts, what you'd have to do is you'd have to take this one here, divide it by 100 millivolts, multiplied by your own specification, let's say 25 millivolts. That gives you the AC component. Then if your DC component was, let's say your DC was 2.2, you take that multiplied by 2.2, and then the sum of the two is just that, add this. So that gives you the signal that you can work with then. So obviously if you want to put this into LT Spice, you'll have to take away these 4 columns, and the easy way to do that is just, I've copied and then I've pasted again, so Control C, Control V, paste only the values, and then you can easily just delete these. So that's what you're going to use as your PWL input to generate the 60 beats per minute. And for the normalized, I've given you 60, 90, 120 and 50, and we will test at a few different beats per minute when we do the testing.